this video I'm going to go over the basics of equilibrium. So far in chemistry, when we have a reaction, we've always assumed that it only goes in one direction and it goes until completion. However, for a lot of reactions this is not the case. So say we have this reaction here with H2O and CO forming H2 and CO2. So if we start by mixing just H2O and CO, then the forward reaction will proceed, consuming these reactants H2O and CO to produce H2 and CO2. So as these products, H2 and CO2 accumulate, eventually there are enough of them to start the reverse reaction. And so the reverse reaction consumes H2 and CO2 and produces H2O and CO. So we have the forward reaction and the reverse reaction happening at the same time. And eventually they'll reach this state called chemical equilibrium. And so at equilibrium, the rates of the forward and reverse reaction become the same. So H2 and CO2 are changing into H2O and CO at the same rate that H2O and CO are changing into H2 and CO2. So even though these reactions are still happening, since their rates are the same, it looks as if nothing is changing. And the reactions of all of these species remain constant with time. So here you can see a graph of the concentration of the reactants and products with time. So to start out, we have a lot of reactants, and then as the forward reaction proceeds, the concentration of the reactants decreases while the concentration of the products increases. And then at equilibrium, the concentrations of both the reactants and products remain constant. And here we have a graph of the forward rate and the reverse rate. So when we start out, we have a lot of the reactants, so the forward rate is very fast. But as the concentration of the reactants decreases, the forward rate decreases too, while the reverse rate increases because the concentration of the products are increasing. And then at equilibrium, these forward and reverse rates will become equal, which allows the concentrations of all these substances to remain constant. So if we have any equilibrium reaction, which we represent by this double arrow, with reactants A and B, and then products C and D, where J, K, L, and M represent the coefficients of these chemical species, then we can write what's called an equilibrium expression. And the equilibrium expression is K, which is called the equilibrium constant, is equal to the concentration of C to the L times the concentration of D to the M, all over the concentration of A to the J times the concentration of B to the K. So you put the concentrations of the products on top of the concentrations of the reactants, and each of these is raised to the power of its coefficient. And so these brackets represent the concentrations of these species at equilibrium. And K is the equilibrium constant, which is always the same at a given temperature. So for example, at 45 degrees Celsius, the K for one reaction will always be the same. The only thing that can change the K value for a reaction is a change in the temperature. So if we flip a reaction, then the new equilibrium constant will be the reciprocal of the original equilibrium constant. So here we flip the reaction, so now C and D are the reactants, while A and B are the products. And so the equilibrium constant of this reaction is the reciprocal of our original equilibrium constant for this reaction. If we multiply a reaction by some factor of n, say we double all the coefficients, then the new equilibrium constant will be the original equilibrium constant raised to the nth power. So if we multiply all the coefficients by 2, then the new equilibrium constant will be the original k squared. And then last, if we add 2 reactions, then the equilibrium constant of the new reaction will be the product of the original equilibrium constants. So if we have some reaction with an equilibrium constant K1 and then another reaction with an equilibrium constant K2, and then we add these 2 reactions, the overall equilibrium constant for this new reaction will be K1 times K2. So let's look at an example. So here we have 4NH3 plus 7O2 forming 4NO2 plus 6H2O. So the equilibrium constant, remember we do products over reactants, and the concentration of each species is raised to the power of its coefficient. So we have the concentration of NO2 to the 4th power because of this coefficient, then times the concentration of H2O to the 6th power, divided by the concentration of NH3 to the 4th power, times the concentration of O2 to the 7th power. So if we have these equilibrium concentrations, NH3 is 0.05 molar, O2 is 1.2 times 10 to the negative 5th molar, NO2 is 0.02 molar, and H2O is 0.001 molar. So these numbers represent the concentrations of each species after this reaction has already reached equilibrium. So if we have these numbers, then we can calculate the value of the equilibrium constant at this temperature. So to do that, we just plug the concentrations into the equilibrium expression, and we get that K is equal to 7.1 times 10 to the 14th. And notice that the equilibrium constant does not have any units. So here we have another reaction, and notice how this is just this same reaction multiplied by 2. So remember, if we multiply by a factor, the new equilibrium constant will just be the original raised to the power of that factor. So here we multiplied the reaction by 2, so the new equilibrium constant will be the original K squared. So the equilibrium concentrations of all these species in a reaction will depend on the amount of reactants and products that you initially mix. But the ratio in the equilibrium expression will always be the same. It will always equal that equilibrium constant, assuming the temperature is the same. So while there is only one equilibrium constant, there are an infinite many possibilities of different sets of equilibrium concentrations. And each set of equilibrium concentrations is called an equilibrium position. So if we have a K that's very large, then we know that there are much more products than reactants at equilibrium. And this means that the reaction basically goes to completion. And if this is the case, we say that the equilibrium position is further to the right. It's more heavy on the product side. On the other hand, if K is very small, then that means the reaction barely occurred, and we say the equilibrium is further to the left. it's very reactant favored. So if we have an equilibrium involving gases, then in addition to the concentrations, we can also describe it in terms of the partial pressures of each gas in ATM at equilibrium. So if we have this reaction here, then we can either write the normal equilibrium expression with these concentrations, or we can write another one in terms of the partial pressures. The rules for writing it are the same. The only change is that we use the partial pressure instead of concentration. And so the equilibrium constant, if we write it in terms of pressure, is called Kp. And remember that Kp and the normal K are different. So to convert between the two, we have to use this equation. Kp is equal to the original K, which is in terms of the concentrations instead of pressures, times the universal gas constant, times T in Kelvin, raised to the power of delta N. And delta N is the sum of the coefficients of gas products minus the sum of the coefficients of all the gas reactants. So for example, in this reaction, the coefficients of the products is 2, and then the coefficients of the reactants is 2 plus 1 is 3. So delta N would be 2 minus 3, or negative 1. So heterogeneous equilibria refers to an equilibrium reaction that involves more than one state of matter. So if we have pure solids or liquids in a reaction, we do not include them in the equilibrium expression. Now this is because their concentrations are basically constant. So if you have some solid block here, if the moles of the solid decrease, then the volume of the solid will also decrease, such that the ratio of the moles to volume, which is the concentration, will always stay the same. So we don't include solids and liquids in our equilibrium expression. We only include aqueous and gas states. So if we have this reaction, COCO3 solid forms CaO plus CO2 gas. Since these two are solids, the equilibrium expression will only have CO2 in it. So the last thing we're going to look at in this video is the reaction quotient. And the reaction quotient is just applying the equilibrium expression to a set of concentrations that aren't at equilibrium. So this is useful if we want to know, so we can plug the initial concentrations of reactants and products into the equilibrium expression, and based on the reaction quotient, we can find out which way the reaction will shift to reach equilibrium. So if the reaction quotient Q is equal to the equilibrium constant K, then we know that the system is actually already at equilibrium and no shift will occur. If Q is greater than K, then that means there are too many products, because remember the numerator of the equilibrium expression is the concentrations of products. So if there are too many products, then the reverse reaction must increase until equilibrium is achieved again. So we say the system shifts to the left because it begins producing more reactants while consuming products. If Q is less than K, then that means there are too many reactants, so the forward reaction must increase until it achieves equilibrium. So we say the system shifts to the right. It produces more products while consuming more reactants. So if we have this reaction here, and the K is this value. And so when we mix these initial concentrations of gases, we can use the reaction quotient to predict what will happen. So we write the equilibrium expression, but instead of plugging in the equilibrium concentrations, we plug in these initial concentrations. And so we get that the reaction quotient is much larger than the actual value of K. And so that means there are too many products, and the system will shift to the left, producing more reactants while consuming products until the equilibrium is established, and this ratio will equal K.